everyone, I'm Professor Harrison, and welcome to our module on statistical inference. In this video, we're going to be covering the foundational ideas that the entire module rests on: population and samples, what separates a valid sample from a biased one, and specific type of bias that shows up constantly in financial data. Throughout this module, we're going to be following a character named Bess. Bess is a financial investigative journalist, and she's covered everything from financial fraud, insider trading, all the way to market misconduct. Her job is to take complex financial data, ask the right statistical questions, and write about what she finds to her readers. She approaches every case the same way: figure out what the data actually says, then see if that data is consistent with what her beliefs are. Between assignments, she keeps circling back to an old investigation she can't quite close. Today, she's starting fresh with a new case: an asset manager whose performance record looks almost too good. To figure out what's going on, she opens her file on the case. Before we can build any of the inference tools in this module, we need to be precise about something that seems basic but ends up being the source of a lot of confusion and a lot of fraud. The population is the complete collection of all units we want to draw conclusions about, every single one of them. The sample is the subset of those units that we actually observe. We almost never have access to the full population, so we work with samples. We collect data on a manageable subset, calculate a number from that subset, and use it to estimate the corresponding characteristic of the whole population. A population parameter is a number that describes the full population. For example, the true average return across every fund a manager runs, or the actual default rate across every loan a bank holds. Parameters are usually unknown. That's the whole problem. We're trying to figure them out. A sample statistic is the same kind of number, calculated from a subset we actually observed instead of from the full population. For example, let's say a fund manager is running around 100 funds. We only have the ability to examine 8 of those funds, however. If we take the average return across those 8 funds, we then can calculate a sample mean. We don't know the true population mean return of those funds because we don't know all the returns of all 100 funds. Instead, we only know 8, so we cannot calculate the population mean. So why do we calculate the sample mean to begin with? Well, the ultimate goal is to figure out what the population mean is, and the sample mean can end up giving us an idea of what that population mean should actually look like. However, this is not necessarily true for all possible samples. In fact, there are many ways to mess up the sampling process to make it so that your estimated mean is very different from that of the population mean. So here's where this starts to matter. A sample statistic, like the estimated sample mean, is only a useful estimate of the population parameter that associates with it if the sample was collected properly. And the standard for collected properly is something we call random sampling. A random sample is one where every unit in the population had a known probability of being selected. Ideally, each unit has an equal chance. That's a simple random sample. The point is that no unit was systematically included or excluded based on something that could distort the estimate. When you sample randomly, your sample statistic ends up being an unbiased estimate of the population parameter. It's right on average across many possible samples. When you don't sample randomly, when something other than chance determines what ends up in your sample, you get what's called sampling bias. Sampling bias is a systematic distortion, not random error. Basically, a consistent push in one direction. The sample ends up representing something different from the population, and any statistic you calculate from it ends up estimating something other than the population parameter. There's a specific version of sampling bias that shows up constantly in finance, which we'll call survivorship bias. Survivorship bias happens when you only observe the units that made it through some sort of selection filter. For example, this could include things like funds that didn't close, the companies that didn't go bankrupt, the strategies that didn't blow up, the ones that didn't survive getting dropped off the sample automatically. So your sample contains only the survivors, and any statistic you calculate from it overstates the true population characteristic. Now let's look at Bess's case. The case involves an asset management firm advertising a remarkable track record. Their marketing materials highlight an average annual return of 18% across the funds that they feature. Potential clients see those numbers and are very impressed. Bess pulls the fund registration filings. The asset manager runs 20 funds in total, but the marketing material feature only features 5 of them. She calculates the average annual returns across all 20 funds. That's the full population. The 5 featured funds average 18%, but the other 15 average just 2%. Working through it, 5 times 18 plus 15 times 2 divided by 20, that's 90 plus 30 divided by 20, a population mean of 6%. The sample mean of the 5 highlighted funds is 18%. The population mean is 6%. That's a 12 percentage point gap between what investors are being shown and what this manager actually delivers across its full book of business. This is survivorship bias in its most direct form. The population is all 20 funds. The sample being presented to investors contains only the 5 that happen to outperform. The other 15 funds still exist, however, they just aren't in the sample. So the sample statistic doesn't estimate the population parameter. It estimates what you'd expect to get only if you ended up picking the winners. Bess explains this to her readers with a single question. If the fund manager showed you the average of all its funds, not just the good ones, would you still be impressed? Almost certainly not. But the marketing materials never give you that number. They give you a biased sample and let you assume it represents the whole. So that's random sampling. The population is the complete set of units that you want to draw conclusions about. The sample is the subset that you actually observe. Population characteristics are parameters, while sample characteristics are statistics. Statistics estimate parameters properly only when the sample was collected randomly. Anything else introduces bias. And in finance, survivorship bias is the specific version to watch out for. When you only observe units that survive some sort of selection filter, your sample ends up being systematically overstating true population performance.